Hello, everyone. My name is Jordan Johnson from Group B, and this is our CDR presentation for our smart parking system. Our group consists of three computer engineers, being Oscar Acuna, M. Ridwan, and Kyle Carpenter, and one electrical engineer, being me, Jordan Johnson. Our smart parking system is a parking garage guidance system that computes what rows have open spots and what rows are fully occupied and directs drivers accordingly. We take a different approach than most parking systems by employing cameras rather than sensors, and the information from this camera will be collected by a website and control unit in real time. It's important to note that this project is only a proof of concept that could be further scaled with more resources. Our motivation for this project comes from the fact that UCF's growing population has led to more cars being on campus. During times of heavy traffic flow, UCF's parking garages become congested, which creates traffic around campus and long lines inside and outside of garages. We have realized that signs indicating open or full do not give enough information about what's going on inside the garage, and we want to make sure that students and faculty are able to enter and leave campus as fast as possible.
Let's go ahead and talk about the goals and objectives. First, we'll be using computer vision, or to be detecting how many cars are passing through a specific region of the garage. And next, we'll be using an LED display to be displaying how many parking spots are available in that specific region to the drivers going by. Next, we want the system to be low power. That's just more in general for our designs. We don't want exorbitant power draw because of bad design, but that's not a super high priority for us because it's not battery driven. We're using an external power supply, so that's not really a problem for us, but even still, just for the sake of good design, we want low power to be a consideration. We also want to be using Ethernet for our communication between our camera, backend server, and the sign display. And the reason for that is it just gives us a lot of configurability options in terms of, let's say, for example, where we put the backend server. We could have it close by, even on the garage, or it could be somewhere else in a remote location. But with Ethernet, we can have those different distances and still have consistent communication between all the devices. For the specifications and requirements, we want the system to be 100% accurate after 60 seconds. But after 30 seconds, we'll allow it to have a little bit of leeway, maybe 90% accuracy. But even still, we're expecting really high accuracy, even 10, 15 seconds after a car has moved into a specific region of garage. So this accuracy is reflecting a car goes in, the camera detects it, and the display shows accurately how many spots are available after the car is pulled into that region and is assumedly parked. For the LED display, we want it to be a minimum of 1000 nits, and the reason for this is 1000 nits is generally considered the benchmark for readable in sunlight. Now, that's not necessarily a big problem for us anyways, because the displays are going to be underneath the ceiling of the garage, so there shouldn't be too much direct sunlight hitting them regardless, making it pretty easy to see. And our display is hitting 1200 nits, so that shouldn't be a problem for us at all. We want the detection to be really consistent in terms of how many parking spots are available, so that we can just have very accurate results on the system overall. For the camera, we want power over Ethernet for the reasons I described earlier, just for the flexibility it offers us. In terms of the division of labor, Jordan's been handling the PCB design. Ridwan is currently handling camera programming, though there's been some fluctuation. He's been currently working on the site. Jordan was originally working on the camera, and then I picked up for a little bit, and now Ridwan is handling that task. For myself, I'm handling the microcontroller and the LED programming, and then Oscar is handling all of the backend with the server, selecting what we're going to be using for our server programming, and all of that.
So this is the overall system diagram for our smart parking project. As you can see, the system is divided in four major components: the camera, the control unit, the PCB, and LED display. The camera allows the computer vision to take place. Through machine learning, the camera determines if cars are entering or leaving a parking area. Now, this data is later transmitted to the control unit through this PoE switch. Control unit server then processes the data and display the necessary information with the help of the created graphics interface. Later, the PCB would receive this data through the PoE splitter, and all the way at the end, the LED display would display the number of parking spaces calculated with the algorithm.
All right, let's go ahead and talk about the camera module. For the camera, it has an integrated video processing unit that allows the computer vision to be done on the camera. This is really useful for us since, unlike other cameras that would result in the computer vision having to be done on the server, this makes it so much better where we can have the camera handling all of that processing and just be relaying how many cars are in a region. So it's just numbers for the backend server to process. It's power over Ethernet, which again makes for easy configurability. Don't need an external power supply. It's just powered directly via Ethernet from the network switch. And it's also pretty easy to set up computer vision using the Depth AI library, since these cameras are associated with Depth AI. Since it uses Python, it's pretty easy to just program and get started at a pretty high level of scripting. There's a lot of examples as well. There's vehicle detection, other kinds of regular object detection for common objects that are already out there, which makes it super easy to get this thing set up. Now, there is a downside for the camera, and is that it's expensive. With the capabilities of having the microprocessor included and able to do the image processing, that does bring on extra costs, but I think this is a worth it cost for us. And as I mentioned earlier, one of the big advantages is that we're able to have the camera do a lot of the processing on its end, relieving the back-end server, and allows for us to have large distance between the cam and server since it uses Ethernet. All right, let's go ahead and talk about the LED display. The display is an LED matrix of 32 by 64 LEDs, which is about 2,048 LEDs, which is a lot if we were doing direct multiplexing. In this case, we are not. So it's using 16-pin ribbon cables for data communication and 4 pins for Molex connections between the interface with the 5-volt power supply. It uses a 1/16 scan rate. This is partly because of the shift registers that it uses in order to address all those pins. If we've been using direct multiplexing, even with, let's say, 144 pin package on our microcontroller, it still wouldn't be enough to address all the pins we wanted. And so because of the shift registers on this display and with the other multiplexing we can set up, it makes it a lot easier to drive these individual LEDs. Also, these displays are daisy chainable, and this gives us flexibility in terms of having the display be double-sided. So if drivers are approaching from 2 different directions and they're wanting to know how one row on the parking lot, how many spots are available, you can have it on either side show how many parking spots are available in that direction. For the display software, the display is pretty simple overall, but as you might imagine, the complexity is not necessarily in the overall design, but in the nitty-gritty with interfacing with the different peripherals. So with the flowchart that we have, it's receiving data from the GMAC interface. The GMAC is basically from the Ethernet. And then from there, I have to process the data from the MAC interface and grab the available parking spot count and then pipe that data over to the display driver. So most of the effort is going to be coming from the display driver. The display driver has to address each individual pixel, and we need to be able to have chars correspond to certain pixels. But then we also need those pixels to correspond to specific pins so that in software, you know, okay, this specific set of pins are for these columns, let's say. So it's going to be a long and kind of drawn out process of just manually configuring, okay, how is each pixel going to display with a certain character, let's say a certain digit.
We decided to design our PCB in a way that it could receive both data and power from the PoE switch. This is accomplished by a PoE splitter as shown in the diagram below, which illustrates the flow of data and power on our PCB after the connection has gone through the splitter. So now we'll go into a bit of detail about some of these components. First, we have the PoE splitter, which separates the PoE connection from the switch into a 12-volt connection and an Ethernet connection, which are then received by an Ethernet port and a DC plug. This 12-volt connection gets further regulated to a 3.3-volt connection such that it can safely power all the components on our board. Next, we have the MPLAB Snap in Circuit Debugger, which allows us to use the serial wire debugging interface on our microcontroller and communicate with the Ethernet 5 chip and LED matrix.
We also have a 50 megahertz oscillator, which generates a clock signal for our Ethernet PHY chip, which then outputs a reference clock signal for the microcontroller. Next, we have the two chips that are on our board being the TLK111 and the ATSAM E70J19A. The TLK111 is a 48-pin chip which serves as a transceiver by receiving the connection from the Ethernet port and then communicating with the media access control block on the microcontroller. The ATSAM E70J19A is a 64-pin chip which includes a MAC block for Ethernet communication and 44 GPIO pins for communication with the LED matrix. Next, we have some of the components that we've used to do some prototyping, being an adjustable buck converter, an RJ45 MAJAC breakout, which gives us access to all the pins on the Ethernet port, and a couple of breakout boards, which we soldered our microchips onto to give us access to all the pins on those. So now I wanted to go deeper into our design, and first we have the schematic for our power input and power regulation circuit, which drops some 12 volt to 3.3 volts. Next, we have the MCU, which includes connections for serial wire debugging, the LED sign, reduced media independent interface, and a single power supply input. And this slide further elaborates on the MCU connections by showing how they are connected to header pins, as we will be using a 2x8 male header for the LED, a 1x8 female header for the debugger, and a 1x2 female header for any situation where we need to erase our device firmware. Next, we have the PHY, which includes connections for the Ethernet port, reduced media independent interface, a single power supply input, and the external 50 megahertz oscillator. And to continue on the connections for the Ethernet PHY, I have the connections for the Ethernet port as well as the oscillator. So this is our breadboard that we've been working on for the past several weeks. And as you can see, some of the components that I mentioned in previous slides can be seen in this photo. And here is a picture of the PCB layout without the copper ground port, so you can see both sides of the board. And I do want to note that we added voltage test points here that were not included in the schematics from previous slides. And here's a PCB with copper ground port, which is also included on the bottom layer, so we don't have to do all the routing for ground connections.
Okay, now let's talk about the hardware block diagram of the control unit. The control unit sits between the camera and the circuit board that controls the LED display. The control unit has a server, it has a Ethernet switch, and a battery backup. Now, remember that the idea is for the camera to detect cars that are entering or leaving a parking area. So let's say, for example, the camera detects two cars entering an area in the parking garage. It will send a data package to the server with the number -2, which means there's two parking spots available less than before. You'll send it through the switch. The server will grab the number, compute the new total available spaces in that area. It will update its local database, and it will send that data to the circuit board or PCB, which will ultimately display that number on the LED display that corresponds to that section. Now let's talk about the Ethernet switch first. To power the cameras and the PCB, we thought that using power over Ethernet would be more cost effective than having traditional electric outlets throughout the garage. So power over Ethernet, or PoE, it's a technology that allows us to inject or transmit electricity into the same cable that transmits the data. Deploying our parking system to an entire garage will of course require a switch with many more ports. But for the proof of concept of this project, a small 5-port switch, it's good enough. There are different versions of PoE. There is type 1 or PoE, type 2 or PoE plus, and all the way to type 4, each providing even more power than the previous version. Now, the camera that we selected requires PoE type 1, which is The standard is 802.3AF. So we searched for PoE Type 1 Ethernet switches, and this is what we found. These are some of the best price ones on the table. We chose the one that is $33.99. Although it's a Type 2 and the camera is Type 1, all Type 2s are backward compatible with Type 1. So we know that it works and we have tested it. Okay, now let's talk about the UPS or battery backup. For a project, we chose a UPS that could keep the system running for about 10 minutes. It can keep the cameras on, the switch on, and the server running in case of a power outage, of course. So the UPS can also communicate with the server to turn it off gracefully in the event of a power outage. Now let's talk about the server itself. We need three things for a parking system: a place where to store the data captured by the camera, a device to relay the data from the cameras to the LED signs, and a program to interact with the parking system, to configure it, to display live data and keep track of available spaces, and much more. In other words, we needed a server that can support a database and that has an Ethernet port, and it has enough CPU and RAM capacity memory capacity to run a custom program. Now, the most cost-effective computers are those that come with built-in CPU and memory RAM built-in, and usually have no expansion slots, such as the Raspberry Pi or those shown in the table. Now, these boards are called single-board computers, and there are many options out there, but not all of them are available right now due to chips availability. Now, initially we had selected the Odyssey board because we could just install Windows, which is what we are using to develop the software. However, this board is not, it's on back order and it's not available now. We may risk not getting it on time. Therefore, we'll most likely go with the Raspberry Pi instead, which is available in kanakit.com. Any of these boards are capable of running Java, which is the program that we chose to write our custom program, and a database for our project. Now, here's the graphical user interface of the parking system program we want to make. Since I have some experience programming in Java, we decided to write the program using Java, of course, and a graphical interface will be done using JavaFX. Now, in this program, we'll want to have a section so we can configure the parking garage. You can see on the left, we have levels, a section, cameras, displays. It's a place where we can add new LED displays, add new cameras, assign IP addresses. We can change or remove things. We also wanted to have a tab where we can see the status of the parking garage, any errors or anything that is going on with it. And live view tab where we can see, you can see it on the right, you can see a live view of a particular camera and how it is detecting and sending data to the database. So this is what we plan to do in Java. And all the parking system data will be stored in a database. Again, I have some experience with Java connecting to my SQL database, so that's why we decided to use this type of database. It's simple. Here are the tables that we are using to store all that data.
One of the goals for the project was to implement a consumer-facing web application. We initially had intended our web application to show the information for parking garages, such as the different levels of garage, the percentage of vacant spots, and the total spaces available. In this picture, you can see what our Figma representation looked like. We also intended our web application to have basic sign-in, creating user, change and forgot password capabilities. Now, through the camera, the live video footage can be uploaded on YouTube, and we actually intended on streaming the footage on the website like this on the left-hand side. And to the right, you can see a page showcasing the informations of the garage and details. Now, at the very end, we intended on having a user page for administrative capabilities. However, due to the time constraints, this consumer-facing web app has been removed. However, if we are left with more time at the end of the project, we intend on making this web app into a reality. This is the summary of our project finances. As you can see, we needed parts for the LED, PCB, and the power supply. However, our most significant and expensive investments were the Oak One PoE camera. Now, onto the constraints. Time is one of the main constraints we faced. Due to the lack of time, a lot of the consumer facing features had to be removed. A larger scale implementation of the smart parking is also not possible for the limited developmental time. The economic constraint is also responsible for this. Now, since the project would be tested in UCF parking garage for the implementation and testing, authorization from the UCF officials would be required, as well as working around the open hours could be a challenge. For a better view of the parking spots, mounting the camera in higher positions must be done with extreme caution. This also brings the concern of sustainability, since Florida heat can damage the system components, as well as bad weather conditions like rain and storm outdoors will pose challenges in the future.
Project completion, you can see the camera and computer vision software is about 30% done. The PCV, LED displays, and the microcontroller software, it's about 35% completed. And the control unit, the server, the software that I'm working on, I'm currently working on the GUI, it's about 40% completed. So for a total completion, project completion of about 35%. Here is a table of standards that impacted our project. And this is our weekly plan to ensure project completion. And thank you. Do you have any questions?